remember that you have an exam at the end of this week over Unit 3. Today we're going to start Unit 4. So this material will not be on the exam. This material, I think, is a little bit more elementary than the stuff that we've been doing recently because we're sort of starting to attack a new type of problem. So hopefully this video will feel a little more comfortable than our more recent topics, and that will allow you to focus on studying for your exam. So I think what I'd like to do as we start Unit 4 is to sort of make an analogy. The first half of Unit 3 was all about solving systems of equations. And remember that what we did first was we decided what a system of equations was, and then we also found some matricial ways of solving that system without even referring to the system. So we had this way of manipulating matrices in order to solve a system of equations. Unit 4 is similar in the sense that we're going to have a certain kind of problem that we want to solve, and then in the second half of Unit 4, we will develop a technique for solving it by using some matrix manipulations. So there aren't any matrices in this lecture at all. So in this set of notes, we're just talking about the kind of problem that we want to solve. Just like in Unit 3, we were trying to solve systems of equations. So in order to state the kind of problem that we want to solve, we have to first talk about graphing linear inequalities. So we'll get started with that. Here, you'll have an inequality that looks something like this one, so y is bigger than x plus 1. In general, what that will define is some region in the plane. So there's going to be a big collection of points that satisfy this inequality, and I just want to shade all of the points that satisfy that inequality. And the general strategy for finding those points is this. We first determine the boundary line. That will be the straight line that you get by just replacing this sign with an equals sign. So we just pretend that there's a quality. And then that line, that boundary line, will separate the points that belong in the solution from the points that do not belong in the solution. So in other words, that boundary line will divide the solution set from the remainder of the points in the plane. So first we graph the boundary line. Usually we graph the boundary line as being solid if there's a non-strict inequality. So if we allow equality, we'll write a solid line. That's because that means that that line belongs in the solution set. And we'll do a dashed line if you have a strict inequality. That's because that boundary line then would not qualify as part of the solution set. So it should not be included in the solution set. And then if you want to decide which side of the line is the solution set, you can just pick a specific test point. It doesn't really matter which one you choose. And then you decide whether that point satisfies the inequality. If it does, then you're looking at the side of the line that should be shaded, and if it doesn't, then you're looking at the wrong side of the line. And then you'll shade the side of the line that makes the inequality true. So let's go through an example here so that you can see what I mean. So I'm going to roughly graph this line. Here we have the line y is equal to x plus 1. A line is determined by any 2 points that live on that line. So you can just plug in 2 x values and figure out the corresponding y values. So for example, we could figure out the y value whenever x is equal to 0. That would be 0 plus 1, which equals 1. So that means that the point 0, 1 belongs on our graph. We can figure out the y value whenever the x value is 1. That would be 1 plus 1, which is 2. So 1, 2 belongs on our graph. And now that we have 2 points, those 2 points uniquely determine a line. So the line that we're looking at will be this line. And now the goal is to decide which side of this line is the solution set. Oh, sorry, this should actually be a dotted line. So this is going to be a little bit messy. But here I have a dotted line. That's because this line does not belong to the solution set. That's just because we have a strict inequality here. So I don't want to allow y to equal x plus 1. I need y to be bigger than x plus 1. So for example, let's try this test point at the origin. So I will test the point 0, 0. So I'll try plugging that into the inequality and seeing if that's true. So I would have the 0 for the y value is supposed to be bigger than 0 for the x value plus 1. This is not a true statement, so this ends up being false. That means that this side of the line does not belong to the solution set. So because the origin lives on the right side of this line and does not satisfy the inequality, that means that the set of points that do satisfy the inequality are the left side of this line. So I've now shaded the solution set. The solution set includes everything that lives over here to the left side of this line, but it doesn't include this boundary line itself, just because of the strictness of the inequality. Okay, so now we'll do something similar here. In this case, I want to introduce a way of graphing the boundary line in sort of a speedier fashion. So a lot of the inequalities that we're going to work with are going to look similar to this one in the sense that they have both variables on one side of the inequality sign and then a constant on the other side. That's just usually the presentation that we'll use for the kind of problem that we're going to talk about in this unit. So this is sort of a typical boundary line to have to graph. And the way that I would like for us to find the boundary line in this case is similar to the strategy that I used in this first problem. Whoops. Remember that in the first problem, I just identified 2 points that live on the boundary line, and that determines the boundary line. So I'm going to do the same thing here, except in this case, I have a bit of a shortcut. The 2 points that I'm going to find are going to be the x-intercept and the y-intercept. And the way that we find those is by setting one or the other of the variables to equal 0. So I would say if y equals 0, that means we're looking for the x-intercept. That would mean that 2x is equal to 6, and that means that x is equal to 3. So that means that the point 3, 0 belongs on the line. And then to find a second point that belongs on the line, I'm just going to set the other variable to equal 0. So I would say x equals 0. Now we're looking for the y-intercept. That would mean that negative 6y is equal to 6. And then dividing by negative 6, we get that y is equal to negative 1. So 0, negative 1 also belongs to this line. Now in this case, because we have a non-strict inequality, we do want the boundary line to be part of our solution set. So that means that our solution set would include this boundary line. Sorry, I can't draw the line very precisely on the tablet, so I'm just going to be kind of messy here. So this is our boundary line. And now we need to determine which side of this boundary line needs to be shaded. In other words, which side is actually the solution set to this inequality. And just to emphasize, what I mean by the solution set to this inequality is the set of points x, y, such that if you plug in their x and y values, then this becomes a true statement. That's what it means to be part of the solution set. So I just want to know which x, y's would qualify to make this statement a true statement. Normally, I like to, if you have a dividing line that misses the origin, I like to just use the origin as my test point, because it's generally easy to observe whether or not that makes this inequality a true inequality. So if I plug in a test point of the origin, then what I would get is 0 minus 0 is supposed to be bigger than or equal to 6. That's false. So again, the origin side does not belong in the solution set, and therefore the solution set is this underside. So it would be all of this stuff down here. So this is how we graph an inequality. To graph an inequality, you're just looking for all of the points that do satisfy this given inequality. And just to demonstrate that these points down here actually are part of the solution set, maybe let's look at this point, which is 0, negative 4. So the point that I've just heavily shaded is 0, negative 4. If we plug that into the original inequality, I would get 0 minus 6 times negative 4 is supposed to be bigger than or equal to 6, and that is a true statement. And you would find that this property holds, or this inequality holds, for every point in the shaded region. So that's what we're doing, is we're just identifying the solution set to these inequalities. So we're going to continue that, but this time we're going to look at a system of linear inequalities. Now, just like with equations, if you want a system of linear inequalities, then you want each of those inequalities to be satisfied simultaneously. So that's what we want to do here. So what I'll do is I will graph each of these lines separately, and then we'll decide which region satisfies all of the inequalities at the same time. So this would just be the intersection of all of these solution sets. So what I'll do is I'll start by graphing these top 3 lines. So maybe before I do that, let me just point out that saying that x needs to be positive and, well, non-negative, and y needs to be non-negative is just saying that we're in this first quadrant region. So those bottom 2 inequalities are happy as long as we live in this first quadrant. So I'm going to mostly ignore those bottom 2 for now, and I'll focus on just graphing these top 3. So we'll graph these using the same strategy that we did a second ago. Sorry, that's kind of light, so I think I'm going to change this color. Okay, so I'm going to graph the top line, the top boundary line, using this color. So here we have 5x plus y is supposed to be bigger than or equal to 20. So because all of these are non-strict inequalities, I will be including the boundary lines in the regions that I'm going to consider. And then at the end, I'm going to intersect all of the boundary regions to figure out what they have in common. So we'll start with this one. Now, rather than showing all of the work for these, I'll show the work for the first one, and then we'll try to do the rest of them mentally. So for this first one, if I set y equal to 0, then what I would get is 5x is equal to 20 for that boundary line. And that means that if we divide both sides by 5, we would get a corresponding x value of 4, which means that the point 4, 0 is on that top boundary line. So I'll go ahead and plot that point. That would be here. That's 4, 0. Similarly, if we set x equal to 0, then the equation that results would be y equals 20. So we can immediately see that the y-intercept is 20. That would live way up here. So that means that the first boundary line that we're looking at is this one. So there's our first boundary line. And what I'd like for us to start doing is we'd like to be able to omit this portion. It's okay if you ever need to pause the video and just write out this scratch work, then that's totally fine. But notice that those computations can be done relatively easily by just staring at the original inequality and pretending that there's an equal sign in the middle. You're just destroying one or the other of the variables and then solving for the value of the remaining variable. So in this original inequality, I can pretend that y is 0 and that the inequality sign is an equal sign, and then it's clear that x needs to be 4. So that gives me one intercept, and then if I instead set x equal to 0, it should be clear just from looking at this inequality that the corresponding y value would be 20. So I'm going to do the same thing for these others without actually writing down the scratch work, but if you start to get lost, feel free to pause the video and try to graph the line yourself. So next what we'll do is I will switch colors. I'm actually going to switch to this one. And now I'll do this inequality in red. So now what we'll do is we'll plot x plus y equals 12. So pretend that there's an equal sign there. If y is equal to 0, then x would be 12. So that gives us 1 point on that line. And if x equals 0, then y would be 12. So that gives us a second point on that line. And that means that this is the boundary line that we're looking for. And by the way, you can immediately determine which side of each of these lines should be part of these regions, should be part of the solution sets, or you can save that to the end. It doesn't really matter which one you do. The strategy that's written up in the notes is just to first draw all of the boundary lines and then check which regions should be shaded. But you could start shading some of the regions now. That would be fine. Okay, so now we'll look at another one. So maybe I'll do this one in green. Now for this one, pretend that this is an equality so that we have x plus 3y equals 18. Then if x is equal to 0, then y would have to be 6. So that means that we have a y value of 6 as our y-intercept. That would be this point up here. And then similarly, if y equals 0, then x would be 18. So that would live way over here. And that means that the region that, or rather the line that we're looking at for our boundary line is this one. So our boundary line is something like that. Okay, and now what we'd like to do is we'd like to determine which region satisfies all of these inequalities simultaneously. So I think what I'll do is I will go back through the colors here, and we will decide which side of each of these inequalities should be shaded. So notice that maybe let's look at this first one. So we'll look at this first inequality. We've already drawn its boundary line, so now we just need to pick a test point. And because none of these boundary lines include the origin, let's just pick the origin as our universal test point. So I'll test whether the origin satisfies each of these inequalities. So if I plug in 0 into the first inequality, 0, 0, then our x value would be 0 and our y value would be 0, and that is not bigger than 20. So that means that the side that should be shaded for that first inequality is the one that's to the right of this first bar. And then we can do the same thing for the red region. So I'll speed things along and sort of skip, but we'll plug in 0, 0 again. So that would be 0 plus 0 is supposed to be bigger than 12. That's also false. So that means that the region for the red inequality should be this region, the one that lives above the red line. And then similarly for this last one, we're looking at x plus 3y is supposed to be bigger than 18. The origin does not satisfy that inequality, and therefore the origin does not belong in the solution set for the green. So the solution set for the green would be the region above the green. So that means that we're looking at this region for our solution sets. And lastly, because we're looking at a system of linear inequalities, what we really want is the intersection of all of these regions. And remember that we had two other inequalities that we talked about at the very beginning. Those just say that you need to remain in the first quadrant. So if I draw the boundary of the solution set for the system, the boundary would be this, the y-axis, because we have to keep an x value that's bigger than or equal to 0. And then the boundary would go along this line, and then along this line, and then along this line, and then along the x-axis, because we have to keep our y values bigger than or equal to 0. So the intersection of all of the solution sets here would just be this big region up here at the top. And that's how you find the graphical solution to a system of linear inequalities. You just need to decide which region belongs to the solution set for each inequality simultaneously.